Picture Earth as a vast, breathing sphere wrapped in invisible energy lines, each one pulsing gently like strings on a cosmic instrument. These invisible threads form what scientists call the magnetosphere, our planet's magnetic shield, woven tightly around us and stretching far into space like a shimmering cocoon. Most days, this magnetic field hums quietly, guiding solar particles safely around Earth the way wind moves around a mountain peak. But every now and then, the calm rhythm is broken. The sun, our star and life-giver, suddenly decides to strike a louder note. A coronal mass ejection, CME, a massive eruption of plasma and magnetic energy, bursts from its surface, racing toward Earth at millions of kilometers per hour. When that blazing cloud collides with our magnetosphere, it compresses and electrifies it, transforming the calm hum into a storm of energy. This is what scientists call a geomagnetic storm, a planetary scale disturbance that can shake the very fabric of our near-space environment. When such a storm begins, it's not just a flicker on scientific instruments, it's a global electrical event. Satellites feel the charge first. Sensors record sudden magnetic surges, and far above the poles, glowing curtains of aurora begin to dance. It's as if the planet's upper atmosphere has come alive, painting the night sky with color while deep underground, electric currents ripple through power lines and communication systems. The KP index, one of the measures scientists use to track these storms, starts climbing sharply. Magnetic readings fluctuate wildly, and the Earth's ionosphere, the region of charged particles above us, thickens and shimmers like a living ocean of plasma. All this happens because the sun has pushed extra energy into our planet's magnetic field, charging it like an overfilled capacitor that can take hours or even days to settle down. The recent storm that opened this month has already shown us how powerful these interactions can be. For nearly 3 days, Earth's magnetic field has been vibrating like a struck bell, refusing to return to quiet equilibrium. Space weather monitors have reported extended disturbances, meaning the energy injected into our magnetosphere is still sloshing around, bouncing between the radiation belts and the plasmasphere. These layers, filled with high-energy electrons, can grow, unstable under such stress, causing waves that scatter particles in every direction. It's a delicate dance of physics happening above our heads, invisible yet profoundly real. What begins as a bright solar flash, millions of kilometers away, ends as subtle electrical whispers felt across the entire planet. So when scientists warn that more CME waves are on their way, it's not exaggeration, it's preparation. The magnetosphere remembers. Even after the first storm fades, the system stays charged and primed. A second or third solar impact could amplify the response dramatically. Each new arrival could turn the calm of space into another crescendo in Earth's magnetic symphony. When the sun sends not one, but several bursts of plasma in quick succession, space becomes a stage for a rare and intricate performance. Each coronal mass ejection, CME, carries its own magnetic structure. And when they follow one another, they form a kind of cosmic relay race. The first wave strikes and weakens the magnetic defenses. The second, riding in behind it, finds a magnetosphere already charged and distorted. By the time a third wave approaches, Earth's field is like an instrument tuned too tightly, resonating with leftover energy from the earlier impacts. Scientists call this magnetospheric preconditioning, a fancy way of saying that space remembers what happened before. When the system is already vibrating, even a smaller push can trigger a much stronger reaction. According to current forecasts, multiple CMEs are expected to brush past Earth in close sequence this month. Think of them as solar waves breaking upon the shores of our planet's magnetic field. With each impact, energy is transferred through vast electromagnetic processes. The radiation belts, which hold trapped electrons circling Earth, become unstable. Some particles are flung outward into space, while others plunge toward the atmosphere, igniting auroras that can spill far beyond the polar zones. The plasmasphere, a region of cooler, denser plasma, also shifts and reshapes under these conditions, expanding, eroding, and refilling in cycles. All this unseen activity translates into ground-level consequences: shortwave radio disruptions, satellite drag, and fluctuations in GPS accuracy. But the story doesn't end with the, sun. There's another player, the moon. During its orbit, our lunar companion occasionally drifts through Earth's magnetotail, the long magnetic shadow that extends millions of kilometers away from the sun. When this happens, near the time of a full moon, the lunar surface becomes electrically charged. The side facing the sun turns slightly positive, the far side slightly negative. This creates subtle electric fields that interact with the plasma environment surrounding Earth. The effect is minor, barely a whisper, compared to the roar of solar wind, but in science, even small changes can matter. When a CME reaches Earth while the moon sits in that magnetic tail, the combination can slightly enhance certain geomagnetic responses, almost like adding a soft echo to an already loud sound. This doesn't mean the moon causes storms, it doesn't have that power, but its position can shape the way our magnetosphere breathes during a solar event. At times, sensors record faint upticks in indices like AE, auroral electrojet index, or DST, which track disturbances in Earth's magnetic field. These shifts are small, yet measurable, a reminder that the Sun-Earth-Moon system operates as a connected triad, not three isolated bodies. The beauty of this interaction lies in its precision. Every charged particle, every magnetic twist follows the laws of physics, weaving a story that has repeated for billions of years. And right now, as our planet stands under a restless star, that story is preparing to write another luminous chapter across the polar skies. Predicting a geomagnetic storm is like listening for thunder long before you see the lightning. The first clues come from spacecraft stationed at the Lagrange Point 1, L1, a silent outpost about 1.5 million kilometers between Earth and the Sun. Satellites such as ACE and DSCOVR sit there, measuring the solar wind speed, density, and magnetic direction. They are our early warning system. When their instruments detect a surge of plasma moving, fast and carrying a southward pointing magnetic field (BZ), scientists know that Earth's magnetosphere is about to open its gates. That southward orientation allows solar particles to directly merge with Earth's magnetic field, injecting energy deep into the system. If, on the other hand, the field is northward, most of that energy simply slides past us like a breeze against a closed door. The tricky part is that the internal magnetic twist of a CME can't be seen until it's right at L1, leaving forecasters with only about an hour's notice before impact. When the shockwave hits, the data starts to sing. Magnetometers around the world record sharp dips and surges. The KP index spikes, and satellites detect storms of charged particles streaming through their orbits. In low Earth orbit, spacecraft can experience increased drag as the upper atmosphere expands slightly due to Joule heating, the process by which energy from the geomagnetic storm warms the thin air, hundreds of kilometers above us. Navigation systems like GPS can flicker or lose precision for minutes at a time, and radio operators notice their signals bending or vanishing as the ionosphere becomes turbulent. Meanwhile, in polar regions, commercial aircraft sometimes reroute their flights to avoid high radiation levels and communication blackouts. It's space weather in action, unseen, unpredictable, yet profoundly tangible. Scientists track all these changes in real time using a blend of ground sensors, satellite measurements, and complex magnetohydrodynamic (MHD) models. These models visualize the invisible, how the solar wind wraps around Earth, how currents surge through the ionosphere, and how energy redistributes through the radiation belts. It's a kind of cosmic weather map, except the storms here are made of plasma and magnetic fields instead of clouds and rain. When multiple CMEs arrive close together, these models show how their shock fronts can interact, amplifying or canceling each other depending on their polarity. This is why even a moderate solar eruption can suddenly trigger a G3-level geomagnetic storm if conditions align just right. While the science behind these storms is deeply technical, the way they reveal themselves to us is nothing short of poetic. At high latitudes, the auroral ovals expand and ripple. In one hemisphere, the skies blaze green and violet, while in the other, red curtains shimmer like glowing rivers of light. For those standing under them, it's a spectacle of nature. For scientists, it's data, living, glowing proof of magnetic reconnection at a planetary scale. The universe is writing equations across the sky, and Earth is both the canvas and the instrument. Whenever a powerful solar storm unfolds, headlines begin to flare almost as brightly as the sun itself. People notice that an earthquake has struck somewhere in the world or that a volcano has rumbled to life, and it's tempting to draw a line between the two events. After all, both seem dramatic, both release energy, and both happen around the same time. But timing is not the same as causation. The truth, as scientists emphasize, is far quieter and more grounded. The forces driving tectonic activity, the shifting plates, the deep convection currents in Earth's mantle, operate over scales of millions of years and involve pressures so immense that the tiny electromagnetic disturbances from space, weather barely register against them. Geomagnetic storms may shape our skies and affect satellites, but they do not tug at fault lines or trigger quakes. Studies have looked for consistent statistical connections, and while a few minor correlations have appeared, no reliable causal link has been proven. In science, interesting is not enough. Evidence must be repeatable and measurable, and for now, the sun cannot be blamed for shaking the ground beneath our feet. What the sun does control, however, is equally astonishing in its own right. Every CME, every flare, every shimmering aurora is part of a vast, predictable cycle. We are living through solar cycle 25, a period near its maximum when sunspots multiply and eruptions become more frequent. These outbursts are not signs of chaos. They are the rhythm of a living star breathing magnetism into space. When those pulses reach Earth, our magnetosphere answers like a resonant drum, converting solar fury into terrestrial beauty. And while we watch, measure, and sometimes worry, we are also participants in this ancient dance. Each flicker of the aurora is a signature of connection between our planet and its parent star. That's why scientists and space weather enthusiasts urge curiosity over fear. Rather than dreading solar storms, they invite people to observe them, to watch the charts of solar wind, speed, and magnetic orientation, to compare them with the glow in the night sky, to understand that what we see is physics in motion,